Hey everybody, this is Rhett. In this video, we'll be looking at the critical value method for hypothesis testing. Here's the essential idea of hypothesis testing. When the observed value of the statistic, whether x bar, p hat, or some other statistic, is extreme in the sampling distribution that assumes h naught is true, we reject h naught. Otherwise, we fail to reject h naught. But how do we define extreme? One method utilizes critical values. That's the critical value method. Let's see how that works. A critical value depends on several things. The first thing we should consider is the distribution of the test statistic. If the test statistic follows a standard normal distribution, then we should use a critical value of z. In other words, z critical. If the test statistic follows the student's t-distribution, then we should use a critical value from the t-distribution. In other words, t-critical. If the test statistic follows some other distribution, then we should find a critical value from that distribution. A critical value also depends on the level of significance for a test. In other words, alpha. And finally, a critical value depends on the type of test, whether it's left-tailed, right-tailed, or two-tailed. Let's focus on hypothesis test for the population mean, mu. If sigma is known, that's the population standard deviation, then the test statistic will follow a standard normal distribution, and we should use a critical value, z. We'll have to choose a level of significance. We usually fix the level of significance at a small probability, such as 1%, 5%, or 10%. In order to determine the direction of the test, we'll look at the sign in the alternative hypothesis. If it's a less than sign, we'll have a left-tailed test, in which case we'll end up with a negative critical value of z. If the sign in the alternative hypothesis is greater than, we'll end up with a right-tailed test. Our critical value of z will be positive. You can either take the absolute value of z alpha or look up z of 1 minus alpha. And finally, if the alternative hypothesis is a does not equal statement, we'll end up with a two-tailed test. The critical value of z could be positive or negative, and will be z of alpha over 2. To find the critical values, we can use technology. In Excel, we'll use the norm.s.inverse function. The parameter is p. That will either be alpha or alpha over 2, depending on whether we are conducting a one-tailed or two-tailed test. If you're using a TI calculator, the function is inv norm. There are three parameters: the probability, mu, and sigma. If you're looking for z-scores, let mu equal 0 and sigma equal 1. Again, for probability, you'll use either alpha or alpha over 2, depending on whether it's a one-tailed or two-tailed test. If sigma is unknown, we'll use a critical value from the t-distribution, t-critical. We'll still need a level of significance and to determine the direction of the test, whether it's left-tailed, right-tailed, or two-tailed. Again, this depends on the sign in the alternative hypothesis. For a left-tailed test, we expect a negative critical value. For a right-tailed test, we expect a positive critical value. And for a two-tailed test, it could go either way. In Excel, you'll use t.inv. The two parameters are the probability and degrees of freedom. Again, for probability, you'll use either alpha or alpha over 2, depending on whether it's a one-tailed or two-tailed test. In the case of hypothesis test for mu, the degrees of freedom is 1 less than the sample size. In other words, n minus 1. The function in a TI-84 is inverse t. The parameters are the same as for Excel. The critical value defines extreme. In order to compare our test statistic to a critical value, we'll need to standardize the test value. To standardize a statistic, such as x-bar or p-hat, we convert it to a z-score, a t-score, or some other standard score. Here are the formulas to standardize x-bar. On the left, we see the formula for a z-score, and on the right, the formula for a t-score. The only difference, really, is that sigma is replaced by s in the formula on the right. If the standardized test statistic crosses the line that is determined by the critical value, then the sample result is considered extreme and we reject the null hypothesis, H0. Otherwise, we fail to reject H0. Let's look at an example. We want to test whether a population mean is less than 6. The appropriate alternative hypothesis is mu less than 6. The less than symbol in the alternative hypothesis indicates that we'll conduct a left-tailed test. The null hypothesis is the complement of the alternative, thus mu greater than or equal to 6. Let's assume that sigma is known. We'll say sigma is 2. Since sigma is known, we'll conduct a z-test. Let's let alpha, the level of significance, be 10%. We'll collect data, our evidence, from a sample of size n equals 16. Let's say that the sample yields a mean of 6.9. Again, the essential idea. When the observed value of the statistic, in this case x-bar, is extreme in the sampling distribution that assumes H0 is true, we reject H0. Let's take a moment to consider the sampling distribution of the test statistic x-bar. If we assume that the population distribution is normal, then the sampling distribution of x-bar will also be normal. The mean of the sampling distribution is the same as the mean of the population distribution. The standard error of the mean is sigma over square root of n. The assumed value of mu is 6. Sigma equals 2, and n equals 16. So, x-bar is normally distributed, centered at 6, with standard error of 1/2. Let's find the critical value for testing the alternative hypothesis mu is less than 6. Again, alpha is 10%. We determined that this is a left-tailed test, and we're assuming that sigma is known and equal to 2. Since this is a left-tailed test, our rejection region is on the left-hand side, so we're looking for a line that puts 10% of the probability in the left tail. If the test statistic falls to the left of this line, we will reject H0. That leaves 90% on the right-hand side. If the test statistic falls to the right of the blue line, we fail to reject H0. The critical value that separates the bottom 10% from the top 90% is negative 1.28. Our test value is our sample mean, 6.9. In order to compare the test value to our critical value, we'll standardize it. The formula is x-bar minus mu naught over sigma divided by the square root of n. If we substitute in the values and then simplify, the test statistic is 1.8. 1.8 is on the right-hand side in the fail to reject region. The decision? Our test value, 1.8, is not less than our critical value of negative 1.28. Therefore, we fail to reject H0. How do we interpret this decision? The decision is in terms of H0. We fail to reject H0. However, we interpret in terms of H alpha. In this case, there is insufficient evidence that the population mean is less than 6. Recall, we were testing whether the mean is less than 6. Let's switch the direction of the test. In this case, let's test the alternative hypothesis that mu is greater than 6. Our level of significance is still 10%, but this is a right-tailed test. We'll still assume that sigma is known. We want to put 10% in the right tail. We draw a line that places 10% probability to the right and 90% to the left. If our test statistic falls to the right of this line, we reject the null hypothesis. If the test statistic falls to the left of this line, we fail to reject the null hypothesis. The corresponding critical value of z is 1.28. Our sample result again is 6.9. We'll standardize this value. The result is 1.8. 1.8 is to the right of 1.28. It's in the rejection region. Our decision: since z-test is greater than z-critical, we reject h0. What about for a two-tailed test? Consider the alternative hypothesis mu does not equal 6. If our level of significance is 10%, we'll split that, put 5% in each tail. These are our rejection regions. In the middle lies the region where we fail to reject the null hypothesis. The critical values that separate the middle 90% are plus or minus 1.645. Z-test is 1.8, which falls in the rejection region on the right. Therefore, we reject H0. In the case of two-tailed tests, it's convenient to compare the absolute value of your test statistic to the positive critical value. If the absolute value of your test statistic is greater than the positive critical value, then you reject the null hypothesis. When sigma is unknown, we'll use a critical value from the student's t-distribution. For hypothesis test about mu, recall that the degrees of freedom is n-1. For example, let's test the hypothesis mu does not equal 6 at the 10% level of significance using a sample size of 16 and a sample standard deviation of 2. Since this is a two-tailed test, we need alpha over 2, in other words 5%. The degrees of freedom are n-1, which is 15. Using technology, whether Excel or a TI-84, we find the critical value is negative 1.75. However, since this is a two-tailed test, we'll use plus or minus 1.75. Note that this test is a bit stricter than the z-test. We'll need stronger evidence to reject H0. In this video, we discussed the critical value method for hypothesis testing. We looked at z-test and t-test for the mean. We use a z-test when sigma is known and a t-test when sigma is unknown. Another factor in determining critical values is alpha, the level of significance. We also need to consider whether the test is left-tailed, right-tailed, or two-tailed. In the case of a left-tailed z or t-test, the critical value will be negative. In the case of a right-tailed z-test or t-test, the critical value will be positive. In the case of a two-tailed z-test or t-test, we'll use plus or minus. Thank you for watching and have a great day. Until next time, stay real and be rational.